All right, it's on.
Yeah, no, I meant did we get the room now that actually has computers to take the exam?
Not yet.
Not yet. Okay, so we had 111 and 112 in Buki, where we actually have the class, with a one above it and below it, so that I could split you up and half in one, half in the other. And for some wise wisdom choice classroom scheduling, then said, oh, we decided we could find a better place in Willard, where there is no computers, which makes it particularly difficult to take a computer-based course. I suppose everywhere computers are smartphones. To do that, but we're not going to do that. We're going to figure out rooms on the back to that'll be the basic format. I know there's an exam that precedes it. If you can get here to it, the basic format is to set it out. It's going to be a fixed amount of time for the first one, so if you come a little later, we'll deal with that based on once they come. So, at any rate, that's the place. So, I'm not sure if there's like a light on this board somewhere. You would think that that would be standard. That's twice as many lines. Okay. House, low, front, top. There's a lot of things. Let's go with what they have asked. That's enough lighting for the moment. And what I really wanted to do is draw an analogy between an analysis of variance and a t-test. That's the basis of if we had chalk, I actually brought dry erase just in case. But it never dawned on me there might not be chalk in a room with chalkboards.
To bring your
oh, I found one. There's one piece of chalk hidden underneath the eraser. How do I teach it here? Everything's PowerPoint anymore, I guess. Okay. So, the concept of the t-test, you guys, it's not too tough. And I also want to use the format. Put a few things up here that I can push up, and then you can see it as a reference. But if I was to bring it up and say, listen, here's a data set A, and here's the data set B. And this basic idea behind this thing, of the t-test, would be, as a student t-test, is that if you were to look at the variability of the distribution of the data, it gives you an idea of whether or not they're different or not. Not exactly rocket science, okay? So you can do that. You can say, if I'm considering the standard deviation of the two, one or two, that gives you a conceptual, easy way of thinking about, are these different? And it isn't a real stretch of the imagination to go one step further on this and then realize that if I happen to have a second data set, so let's say that we had a different axis here, down below, offset, so it had, let's say, the same variability associated with the A data set. And then the other data set here would be something with thanks. Oh, yeah. Wow. I broke the bank today. Okay. And then there's a lot more variability in the other data set. So let's say that this is now B. That's going to make it harder to figure out whether or not they're different or not. Okay? And so in this case, when you have larger increased variability, which we'll talk today as basically crappy data, right? So if I have crappy data in one of my data sets, okay, then it will be harder to develop if there's a difference. And I'm going to throw in the not a difference thing here, because we all know they're different. We established that last time, that idea, are these 5 and 7 different numbers? Okay. So the hard thing is how to tell if they're not different. So, trying to take this one step further. So this is basically the idea of a t-test. What we're going to be talking about today is whether or not a model fits data. So it's no longer just this easy idea of here's the grades in this class, here's the grades in the other section, are they different, blah, blah, blah. Okay. Instead, it's a way of actually thinking about this thing, where instead what you have is truly one data set in which you have, okay, so now this is ANOVA. And ANOVA, it shakes like crazy. ANOVA, it stands for Analysis of Variance. It says variance. And you can figure out without too much of a rocket science where ANOVA came from. Okay. And it is basically a way in which you then take a look and say, let's say that this is our data, that it's all the data that has multiple dependent variables now. So it's not just simply something that represents a mean. This thing right now here is a composite measure of the variance of the crappiness of the data. Okay. So we'll call it crappiness. I'm not sure if that's how you spell crappiness. Crappiness of the data set. And so you all kind of understand what crappy data looks like, right? So it's that thing is supposed to be a straight line. Okay, it's all over the place. That's crappy data. Okay, not so crappy data would be if they were all like. Okay, and yet it's not just an idea of being around some mean. It's just this composite measure of how good the data set is. And at the same time, then, we need to then create a measure of how well the data fits the model. So the other distribution, if you want to think about it here, is it's a conceptual distribution, and this is how well the data fit, or the model fits the data. Now, similar to the case where you knew that the averages were different, if you really have replicated data and the data isn't always the same, so if I went to here to the same x variable, whatever that happens to be, whether that be time, whether that be concentration of some substrate or something, and if you get 3 different measurements, then of course it's impossible to fit all of the data. You can fit the averages maybe if you're lucky, but you'll never fit all the data because unless your model like to go that doesn't make any sense, okay? And so there is going to be a lack of fit in the model, and how badly it does is going to be a combination of how bad the model is and how bad the data is. And so this analysis of variance concept here is basically associated with this basic idea. So now we go over here, and one of them is chalkboard 1. Seriously, okay. So the next thing I'm going to do is draw a few pictures. This is for real. Is this like an all of them? And I asked if there was any way to touch the button that it would like keep going. Stand here. Let it go up. Okay. So. Now, I'll die before this actually gets up to the top there. What I want to do is give you this basic concept that given a given data set, you can have more than one model. Okay. So let's take a look then at a basic idea of where I have essentially 2 data sets. One that's a pretty reproducible data set and one that's a reasonably crappy data set. And yet they have the same mean. So let's just go like here, this is the same mean, blank, like that. Pretend they're the same. And in one case, you actually have a pretty tight experimental measurements, and in the other one, you have much worse measurements that represent crappier data, if you will. Okay. Now, once you actually have that, so these are the same average y values here. Same average y value on this axis here for both data sets. If I was to go through this thing, then I would have the ability, of course, to fit more than one model to it. So I have model 1, and then I might look at that and say, not too happy with that one. Let's do the model 2 one, okay, right? And that would be model 2. Well, this is really what analysis of variance is all about. It's that basic idea of trying to say something about, number 1, is that model better? Which we know the answer to. How do we know the answer to that? The curve, model 2. Does it look better? Why is it better? The sum of the square errors is less. Okay? You're getting towards the analysis of variance here, but it's just like if it's the data better. Okay. It also has an additional adjustable parameters, right? If it's got curvature, it's more than just simply a straight line. And the more adjustable parameters you have, the better they fit. So we are not really, whereas if you do a typical analysis of variance in like Excel, it will give you the same answer every time. It will tell you that the model is statistically significant. And I'm going to explain in a bit why that's a why in many cases. But the point is here, it can also, if you want to know whether or not it fits the data better, you know that, again, without statistics. It's got more adjustable parameters, it fits it better. Neither of which is terribly exciting. If I was to then put those same models through here, by the way, you'll get the same y equals mx plus b. If the averages are the same, that's something that's a little hard to prove, but we can do that someday before. 1 and model 2. And now it's not so clear whether or not you can justify it, right? Because if you have crappy data and you're looking at that, you might kind of look at it and say, you know what, the straight line might be good enough. That's the fundamental question that I want to try to get to by the end of this class. How to tell whether or not you can justify doing the quote-unquote better fitting line relative to the other one based on the quality of the data. The data is better, then not too surprisingly, it's easier to tell the difference between that. It's called model discrimination. Is the actual, I guess that's probably not even politically correct anymore. I made that up 10 years ago. So we need to call it not discrimination, but diversity. Okay, model. No, it's really discrimination, that the difference between the two, which one's better. Because there are actually a difference between people and models as well. Last time I checked. I did this the first time I kind of tried to come up with this based on this idea I had up here. In terms of what does this mean in terms of what we're going to do with the test. When you did the test like a t-test, you went to some formula and you looked up the standard deviations and you plug them into the formula and calculate the value. You look it up in a table and you see if it's bigger or smaller, and that tells you if it's statistically significant or not. It's very similar to how you do it with an F-test or an analysis of variance, but it's no longer easy to understand where it came from. And I'm trying to sort of get that as we go across here. So if we take a look then at the top one here, and we have, say, some, in this case, let's just call that the standard deviation associated with the crappiness of data. Well, if that's what that one is, well, then this one's going to have to be what? Broader. Okay? Crappy. Okay? So this will be the one associated with the actual data itself. And then if you were to take a look at what's going on here and then ask yourself what goes on if I think in terms of how well it fits the data, well, in terms of how well it fits the data, the straight line doesn't actually fit it that well, right? There's a large variance of what's not being fit. And so it's going to have a pretty broad distribution associated with it. This will be model 1. And the variance of not fitting, so to speak, with model 2 is going to be much smaller. In other words, it's going to be much narrower. And so, you know, at least in your brain, if you can kind of think of this as what's happening when you're doing a model of variance, it'll actually make more sense to you. And so this will be M2, and then you're going to be asking yourself, is what I'm not fitting? Because these variances, these two guys right here, this is the what I am not fitting. And if you think about it, when what you're not fitting starts to look like how crappy your data is, then you can't do any better but with a different model. You can only get as good as, in terms of not fitting, relative to the actual crappiness of the data set. So if you take a look then at this and ask yourself, what about these other two? Well, they both kind of like don't fit very well, right? In a sense, because this data point's pretty far away, and that one's kind of far away from that one. So even though it has curvature, it still isn't like doing that much better because the data's crappy. Okay? And so what you end up with then is a situation where you may have a distribution where you have where M1 and M2 really aren't that much different from each other. They both, and they're comparable to the actual data set. You may actually end up with coming to the conclusion then statistically that this one's good enough. And that's what we're going to go through now is this idea of how do you tell when a model is good enough based on how crappy your data is. That's the basis of the actual lecture itself. Now, the idea of analysis of variance has a very precise definition if you have a linear model. Okay? So this is very precisely defined. If you have a linear model, and I'm going to put this in quotes here because what I mean by a linear model is the statistician's definition of linear here. And probably more importantly for nonlinear models, okay, the approach is good enough. Okay. And I have been here in my notes, I may as well go by them. It works well if the data and the models are reasonable. Now you can imagine, I've gone to the statistics department several times here and then even at other universities. I mean, when you use the concept of are reasonable, they don't like this. What I'm going to go through here, you will not find it, and I've never found it in a statistics book because statisticians are not reasonable. No, they like the world to be linear because, in fact, you can linearize most stuff if you want to, right? You can do double reciprocals, you can take the log of it. Take log of it multiple times. You can make stuff linear if you want to. The problem I have with that basic idea is if you take and make everything linear, then the equations that you decided to make the behavior are getting lost in the logs and the inverses and the other stuff too. So forcing a linear model on stuff doesn't. So what do I mean by reasonable is the next obvious question, right? This gets right to the basic question of what does it mean to be statistically significant? And this is where the disconnect happens for most of us conceptually. So what is statistically significant? So, I suppose I could wait for half an hour for that to move up, couldn't I? Or I could erase things. So I'm going to actually instead use the eraser. Okay. So I'll leave that axis there. It's a nice chalkboard. It actually erases. Okay, I don't like that. That works so well. Where's my chalk? Maybe no. So let's say I now have the data set, and we'll just throw one out here. And this is intended to be a question. So let's say that I fit this with the simplest model of all, and the simplest model y equals mx is be like a correlation type thing, right? And then I was actually come up with that as my fit. Now let's say that I didn't actually graph it, okay? But here, it's now graphed in front of you. And I asked the question then the eagle guy here, is that statistically significant?
Yes.
No. We're not asking if it's different. We're asking is it statistically significant with respect to its ability to fit the data set?
No.
Okay. Which you say that because we'll go next to you. Why would you say that? It looks pretty bad, right? I mean, this is kind of a trick question, but not really. Most of you would be happy with the statement that that's a pretty crappy fit, right? Okay. And therefore, you might think the statistics would tell you that that's not a good model. Okay. But you have to remember that the question being asked is this a statistically significant fit to the data? And what you can ask yourself then is this, let's say that you want $100 an hour, but somebody is willing to give you $20 an hour. And then you were asked the question is that a statistically significant salary being paid $20 an hour? In which case you would say, well, it's a lot more than nothing, okay? And so maybe I would consider working for $20 an hour, even though I really like to. So that basic question, is this a statistically significant, is more like, is it describing a statistically significant piece of the data? And the answer to this is, well, yeah, it's describing like, I don't know, 40% of it. And 40% is a lot more than nothing, right? In fact, if you start to think about what would it take for the model to not describe any of it, it would have to be incredibly crappy, right? Okay, it would have to be like this, right? That would be not statistically significant part of the data set. And so again, this is sort of it's something to be aware of because of the way in which statistics is presented. By the way, if you want to find that precise definition here, that's actually all derived in the statistics training manual. But now, if you take a look at what statisticians and typically run as linear models, a typical model would be like this. Y equals, we'll just give it an intercept because there's always the possibility of being offset. And then they'll have some slope with respect to one variable, and then they'll have some other slope with respect to some other variable. And then it's possible for parameters to actually interact with each other, so that would be x1, x2, plus blah, 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 blah. That's a multiple linear regression model. And that's what is purely defined very precisely by analysis of variance. To give you an idea, where I first really started this to make sense is when I was on a PhD committee in ecology. And they were looking at aphids attacking hazelnut trees. And then asking the question, what affects whether or not the hazelnut tree gets, these are wild hazelnuts out in the woods. Like, man, I so wish I was doing my PhD, walking around in the woods, counting aphids on hazelnuts and calling that, okay, but, unfortunately, I wasn't smart enough to do that. But the parameters were things like, how wet is the soil? What is the carbon content of the soil? How much sunlight comes down from the trees above? All this stuff. And asking if there was a statistically significant effect of that parameter on how many aphids colonize the tree. And now you can start to get what it means in that context here. I'm saying that does that parameter, or does the interaction of that parameter, then seem to describe the behavior that's there? Is it a significant contributor to the observation that I measured? Okay, not is it a good model in the sense of the way we think about models. We think about it like as it goes through the data. Okay? And that's what you'll find if you do the automatic analysis of variance in Excel. And the answer to that is always the same. So Penn State up there. So try to reiterate to me, what I'm getting at here. Why is the model always significant?
Because it fits some of the data.
Because, how often do we as chemical engineers have a model that's so bad that it doesn't even show up on our graph? Okay, now, sometimes we hand in homework that way, okay? But that is not reasonable, okay? And so we tend to be highly deterministic in how we look at these things, and we find that rarely do we have a situation where the model is not significant. And that becomes something that is very useful to understand, because it allows you a nice internal check. Every time you do an analysis of variance the way I'm showing you to do it, it should always give you the same answer. The model is significant. As long as your graph is anywhere near the data set, okay? Whatever it happens to be, and then I do my model or whatever through this thing. So basically what you have is that chemi tends to work with fitting models and not asking questions like, hey, does temperature contribute to the vapor pressure of the fluid? Oh yeah, it does. Okay, we're not going to ask that question. We're going to ask ourselves here, I have an equation, and we're going to do it. The downside of that is we don't tend to write things like this, the multiple linear regression. We instead tend to have nonlinear relationships. And once you start to do nonlinear things to this, that nice proof that is inside that, which it'll come up again a little more mathematically in a minute, doesn't necessarily hold anymore. And so that makes a statistician really, really nervous. When you start to teach how to use statistics, that there's no rigorous proof for it actually working. And it doesn't make me the least bit nervous to teach things for which there is no rigorous proof. So, what we're going to do next, why not, is we're going to actually, oh wait, it's a race. Okay, so we're actually going to go through a little bit of the mechanics. It really is. Of setting up an analysis of variance table, but not, okay, so there's the one. And once you set up an analysis, I'm going to yell, I'm going to fall asleep here. I guess it's not so mathematically. Okay, they couldn't actually put a logic switch in there. So setting up an analysis of variance table, my problem with just giving you one is that what I find is students are really good at cloning spreadsheets. And I could just give you one that had it all set up in that, and all of you are either boys or ever actually trying to understand what the elements are in the table. Because you grab the right one, and then you put your XY data set here and there, you clone it into the scenes of the spreadsheet, and so I'm purposely not giving you a prefab analysis of variance table at this time. Because I do want you to understand what's going in the table. So let's go with, here's our data set, and over there I'm going to set up our table. Now, we'll go with a straight line because it makes us all reasonably comfortable. That, okay, so I have 1, 2, let me see here. By the way, you can take more than, all your data doesn't have to be replicated the same. I'm doing that on purpose as well. And let's say that that's my, how many data points was that? That was my 9 data points. Okay, so you can take that and call that one Y1, Y2, Y3, Y4, Y5, 6, Y7. Oh, I lost one somewhere. 7, Y8. It's not going to cause us too much data risk here. some model through it. It's going to look like a straight line. It doesn't have to be, but we'll just call that an equation for the purpose of this discussion here. At this, there's certain places where I took the data. So we'll call that one x1, and then this one here would be x2. And you'll notice they don't necessarily correspond. x3. It was taken at 4 different temperatures, times, whatever the heck it is. And so this represents basically our the data we're going to put into a data set here for an analysis of variance. Now, the mathematics of this are that the sum of what we refer to as the residual, that's the sum of squares, by the way. Okay, so the sum of squares of the residual is going to be equal to the sum of the model, okay? Sum squares of the model, and minus the sum square of the, I'm sorry, total there. So it's the total minus the model. Total minus the sum square of the model. Now, it makes sense conceptually to you until you'll see that there's something missing in here. What's missing is, okay, first of all, this right here, the residual, well, if this is the total sum of squares and this is the model, this is the lack of fit here. This is what, this is like a lack of fit. And there are 2 reasons why there's a lack of fit. One is because the data's crashing, and one because the model might be crashing. Either one of them are captured here in this thing. And so this is the sum of the error. Sum of the squared error. And this is somehow proportional to, no, that's proportional to maybe question mark. Okay, you'll find that in all the math books. The sum of the observations, because the total here, that's easy, right? That's just my y. So I just square them and add them up. I just take each one of these guys and square them. And then I need to then find the model value. Well, the model value is really easy, right? I go to that x, and it's going to be, there's going to be one right there, right? That's going to be y model at x1. So I take that value and I square it, and I square it twice because there's 2 observations at that one. I square it once there, 3 times there, 2 times there, and I add those all up, and so that's going to be minus the summation of the y model squared. And there's a long, this is where that proof is in my statistics training manual, and that is if the model was fit by minimizing the sum square error, then true. And what I mean by true here is that there's something missing from this. Because what is the definition of the error for any given observation? So let's go to the girl in pink. So what would be the error if I took an observation at x1 there for the error associated with trying to fit that based on the model that I have? You don't know? I mean, so it's not conceptually that hard. We're down the road. Well, if I let's say that this wasn't like school, okay? And I ask you, like we're out and we're like throwing at some like tree in the woods, okay? And I ask you like, what was your error versus my error? And then I snowball, I throw at her, okay? What would that be? How far away it is, okay? So it would literally be this, the error would be this distance, right? So this is the model prediction, and that's where it actually was. I mean, that's, you know, I should blow this up, and most of you can get it. It's that was that big, that was that big, that was that big. Okay, that's the error, right? But that error is equal to what? Error is equal to, give me a math term for that. Go ahead. What? Yeah, well, I want the equation given in terms of y.
y2 minus 1.
Okay, so this one right here is going to be y of that 2 minus y average, the y model, right? Well, that y model is going to be, in this case, it's going to be x1 plus b, right? That would be the definition, or if you want to think of it, y. This is kind of like y sub I, y model. In a way, but what if I think about error squared? If I think about error squared, right, that would be this. Well, now, can anyone see what the problem is here in terms of what I'm trying to say, how analysis of variance works, and the mathematics of just simple logic of fitting and not fitting? Let's go to you, Zon.
I bet you the sum of the error squared can be negative.
Okay. Can it?
Yeah.
Well, I'm getting more specific here. Okay, look at the math of this. They look pretty similar, right? Under what circumstances does y sub I minus y model squared equal y squared minus that? Is that a proof that you ever saw in your math book?
Yeah. Y times y multiplied.
Right? Remember, when you do that, you end up with this one and this one. There's a term in the middle, right? Okay? You get to square this guy and this guy, but then there's that other term in there. That term is the one that's the product of 2 times each other minus 2 times it and all that stuff. Okay, where'd it go? Well, the answer is that because you minimize the sum square error, that term has been essentially goes to 0. That's the mathematical proof that takes about 5 or 10 pages in the training manual. Okay, because you can kind of imagine that trying to prove that because you know that is not equal to that, which means this two can't be equal to each other. But under a circumstance where you are fitting it by sum square error, and you have to, you can also do this with matrix algebra if you're really good at with inverting. Remember that a linear regression is basically the inverting of a matrix and all kinds of stuff that happens in your calculator. Okay. You can then prove that missing internal term there goes away. Okay. And that's inherently very important. But the very, very important thing is that if, and only if, you minimize the sum square error. You can't just fit any crappy model and then hope to do an analysis of variance. You can only do it after I fit the thing to it. Okay? And that includes if it was a nonlinear fit or something. You'd have to minimize the sum square error and go through that. But if it is not truly linear, it turns out that it's not exactly true that term goes to 0, so you can get a little bit of ugliness that comes into play. But the ugliness is not so big that it is hard to interpret as an engineer. You're still looking at this thing and asking yourself basic questions of, is there statistically significant not fitting of the data? So let's take a look at what an analysis of variance table actually is. So the table itself is made up where there's a total sum of squares, there's a model, there's residual, where I didn't actually fit it. There's a term that I'll explain in a minute, it's the left out terms. These are the parts that aren't in Excel. And then there's the true error. So in a sense, total, this is kind of easy. This is literally a table that you would create if you were in Excel or whatever. And the top one here would be the sum of squares. Now, let's just see if we're following here, and we'll go to Rachel. Top term here. What do you think the total sum of squares would be in the table? You don't know what I'm asking, so let's get on down here. So what does that term mean? Articulate it in like logic here. How you would use the thing that I gave, the data I gave you. Okay? Yep, that's pretty easy. So you just simply take each y1, y squared plus y2 squared plus y3 squared plus y4 squared, and that would be the total sum of squares. Okay, so this is the point I'm trying to get at. Doing an analysis of variance becomes so easy and mechanical, your brain can go on hiatus. And I'm not interested in your ability to add up the square of 8 numbers. Although it is a challenge for us at times, okay? The idea that I can add up all the observations that I have and square them all is tough. We usually get that one right. Now, the model sum of squares is where I lose about a quarter of you. And it's not because it's all that hard. You want to take a shot at that one? Which is that thing, okay? So you get a 5, okay? If I was just to take my observations here, and model squared, model squared, model squared, model squared, that is half right. Why is it only half right? What? No. Okay, you get 5, 2. Okay. Let's see, it's going to the back. Way in the back there. Okay. Wait, one behind you, so you're not even close to the back. No? Let's go even further back there. What? You listening? You can come down and join us. Okay. Maybe you. Can you see that from up there? Oh. Wow, I hope as a freshman math teacher. Yes, right there.
If there's like 3 data points in one X value, then you have to do it 3 times, add them up 3 times.
Yeah, you got to do it, right? So for this one here, where there were 3 observations, I have to add it up 3 times because there are, in fact, remember, there was 3 observations here. I got to subtract off the model prediction at that 3 times as well. Okay, and so it is, in fact, the sum of the model squared. But you got to be careful to make sure that you take into account that there's more than one observation associated with each one. Easy in a spreadsheet, right? Because there's going to be a different y there, and then it's going to happen again.
So wait, you're saying that you square every term, every point?
Yeah.
So wouldn't that be much, much larger than like all the other ones if you had a lot of data?
Yeah, it's a big, big, big number.
You know, if like normalize it by how many pieces?
Perfect. Lead in. Okay, we get. Okay, so you get a 9 for premonition. Okay, because it's a big ass number, right? And it shouldn't matter too. You know how big this is. It shouldn't matter whether I multiplied it, did it in meters, millimeters, nanometers, or whatever. So there's got to be something that normalizes all this crap. Otherwise, there's no basis for that. So the next column has to do with its normalization. But the basis of the normalization, and okay, I'll say what it is, and then we'll finish the table here, because it's degrees of freedom. Okay. So I'll get to what that means. Is like if I took 20 data points, then your total degrees of freedom is going to be
19.
Good shot. Try. No, it's actually 20. Okay. N minus 1 means, who said that? You probably had stat something, right? So you're used to that subtract 1. I don't know why, but I just do it. Okay. Okay. Maybe now you'll know why you are or are not subtracting that 1, because it is important. Okay. But now, what do you think the residual is? Okay. So we'll go to the girl in the corner over here. Yeah. The difference between? Yes, okay, it's rocket science today. Okay, so we take this one minus that one and we put it in there, right? So it's the summation of the y sub I minus the summation of that. It's just that number minus that number, and we can all do that. That's what, in fact, the residual is. Okay. Now, true error. This one's a little tough. Because what the true error is the measure of experimental variability here. Now, if I look at a data set, what seems to capture the experimental variability that's inherent there? I mean, I've been drawing, of course, the one that did it the best, I erased.
How clustered the points are?
What's that?
How clustered the points are?
Yeah, and go a little more mathematical on that. And
Distance between points at the same.
the size of the error bar. Okay, right? Okay, so it's basically how big the error bar is, right? Okay, and so this thing right here is calculated for kind of like an average error bar size. Because there is no error bar when I only have one, right? There's going to be a different one that has the degrees of freedom there, so it gets a little complicated. But you can kind of think of it like an average error bar. Okay, I just, a couple of statisticians rolled over the grade error bar. It is okay. Degrees of freedom. Okay. Associated. We know what the total is. That's how many in our experiment right here. How many degrees of freedom? Guy right there. If you're not looking at me, I'll yeah. No, that's you. Yeah.
For degrees.
Yeah. For our example, how many degrees freedom? No. How many? I want a number.
8.
Yes, there's 8. Okay. So in this one here, there would be 8 because there are 8 observations. How many degrees of freedom associated with the model? Okay, right here, I'll share it.
2.
Why?
Slope and intercept.
Got y equals mx plus b, 2 adjustable parameters. If it was y equals mx, a correlation, there would be a 1 degree of freedom. Saturation kinetic is the number of adjustable parameters. Now remember that you can have a fixed adjustable parameter that you get from a different data set. Let's say that I knew the Vmax and I knew there was a fixed value and I wanted to fix that, but I wanted to find the Km. I could fix the 1 and make the other variable. That would give me a 1 degree of freedom. It's the number that you are in fact varying that is important for that. So it's the number of adjustable parameters. Parameters. Okay, can you read that? Okay. And what do you think the residual is? Here. Girl likes to rock star. What is it for this problem? I want a number. 6. Okay, 6 because it's 8 minus 2. Okay, because there's 2 adjustable parameters there, there's 8 there, and so this particular one, it's just the difference between the 2, right? So it's 6. What about the true error? Remember, true error is the hard one, so girl in the green hiding behind the guy in the yellow. That's true. Okay. That's exactly what it is. Okay, I want to know what it is. Like, for real. No? Now you know why? Guy in the yellow? Can you help her out? Okay, I thought so for sure you were ignoring me because you knew the answer. Okay, let's keep coming down. No, I lost. Anyone wants to throw away here?
4.
Why? Okay, 4. Good guess. 4.
Just because there's 4.
Because I can give you a 4 out of 10 for that answer. Okay. So, not a great answer, but at least you're on the right track, right? Okay. So let's get better on the track. And why is it not 4? Nope. Okay. It is not 4 because we don't have 4 independent estimates of error. Because the one has only one observation. And so it's equal to the number of error bars that you have, because that's the number of estimates of error I have, right? Okay, so in this particular problem, it's equal to the number of independent estimates of error. Okay? Or, in my simple brain, the number of error bars. Now, there are times that you are going to be fitting like dynamic simultaneous differential equations and junkins that, and I guess it still is the number of error bars, but that's the basic idea here. Now, the next column in this, it's going to finish up pretty soon here. Okay. The next column is this one. Okay. Now, so what exactly is the next column here? Are you listening? Yes. It would be mean square, right? Okay. Let's go. Okay, so we have the mean square is next. Okay. You got that close and still didn't get it. Oh, that's so bad. Okay. So we have the mean square. Is that how we calculate that? Well, we do that normalization that you wanted to do. You just divide this one here by its number. So it's this column is the sum of squares divided by the number of degrees of freedom, so I can start to get some normalization built in here. Okay? It's not really all of the normalization, because that's going to happen when we take the ratio of variances, which happens next. So all of these guys here are just divided by degrees of freedom. It is the summation, it's the sum of squares divided by the degrees of freedom. Okay, and they should all, now you don't have, no, I keep forgetting the left out terms. Okay, the left out terms is the really important one. It's the one that we're going to use to figure out whether or not we forgot to fit too much data based on the quality that I have. Okay, and so whereas this is the residual, here is the total minus the model, this is the true error. This is going to be the true error now minus, it's the residual minus the true error. It is what I did not fit, and that's why I call it left out terms. It's the stuff that I could fit if I had a better model, but I didn't fit because the model wasn't good enough. Okay. So this is the left out terms that are in here, and so it's basically resid how much I didn't fit minus the true error. You know, minus how crappy my data is. Now you can kind of get an idea, right? If I fit any of my data and I did a crappy fit, and my data and my error is crappy, and my real data is crappy, then I don't have much left out terms. Okay, it's only in a situation where I didn't fit it very well, compared to how bad my data was, that this thing starts to get significant. And that's the fundamental question that you want to end up asking, is that, is what I did not fit statistically significant? Because the answer of whether the model is significant is always the same. Unless your data is so, your model is so crappy, it doesn't show up on the graph at all. Okay. So, now if I want to do this, remember what I'm trying to do is I'm trying to compare up there, the very top, the variance, if you will, of the crappiness of the data with the model. But remember that the units of a variance are the square of error. In fact, that's functionally what we've done here. Is our mean square is kind of like a measure of that distribution over there. And so all I need to do is now take the ratio of them. And so you can take a look and say, well, what do I want to test? I can ask the question here, is my model significant? So I take the ratio of this mean square for the model relative to the mean square of the true error. Because that's what I want to compare. If you use the statistics in Excel, it has a tendency to assume that this one and this one are the same. Not very useful. Okay? What I really want to know is how well I fit relative to the actual true error. The moral of that story is, unless you have replicate data, you cannot do a meaningful analysis of variance. And it makes sense, right? If I didn't repeat anything, how the hell can I know whether the model fit it or not? Okay. That basic ratio then will be that this guy here will just, this guy here goes on the top, and this guy here goes on the bottom. Okay. And I end up with a ratio of variances. In a sense, it is a ratio of those two distributions I have at the top of the board. And then you just look it up. This is referred to as the F calculated. And then I look up something in a table. And all this table is somebody mathematically kind of looking at what these things mean, and they give a value. And if the value in the table is smaller than the calculated value, then that thing is significant. And I always forget that. But I don't have to remember it. Why do I not have to remember the criterion? What's that?
You wrote a manually about it already. You can just look at that.
Say what?
You wrote a book thing about it already. You can just look at that.
No, it doesn't matter. If I read a book, I may forget everything in it. Okay, the next time. Okay. No, I know the model's significant, right? So this number, by the way, is always big. It's really, really big. Because experimental error is usually pretty small relative to how bad my model is. Whether if it's anywhere close to the friggin' data set, it's going to be significant. And so I now know that this thing is going to be a pretty big number. And I look up the value in the table, it's a pretty small number, and so it tells me that, oh, big is significant. And so you always get that answer. Unless the absolute worst bizarre situation, your model was nowhere close to your data, this will always be true. Now, to finish off the lecture, all I need is, okay, the girl put her head down, okay, yeah, you, okay, okay. The final test that is the one that is finally meaningful from all of this analysis, what is it? Oh, not you. Okay, you can be, you're plan B.
What were you asking?
Punchline of the lecture. I was asking you, what are we going to compare here to tell ourselves whether or not we have a good model? Well, we know that it's statistically significant, but I proved in the beginning of the lecture that every damn model is statistically significant, so we didn't prove anything. No. Maybe. What? Okay. Okay. We're doing an F test. Okay. Okay. So, no, we don't. It is like a t-test, but it's not nice and neat, easy thinking. What about you? You think, Sean?
Closely correlated to last circle you do as to what you got from the table?
No. Which one?
The circle.
No. It's the thing we haven't done in the table that's important. I just want to see if anyone got where this thing was going. And maybe it's like so close. Anyone want to throw it out there?
All models are reasonable, but it's
True. No, I know that. I told you that. Look how this thing is small. This one is big. Okay, big is bigger than small, and therefore the model is significant. But we knew that before we started the damn lecture that they're all significant. Okay, so that doesn't prove anything. Yes.
How significant it is?
Okay. The stuff down here, right? I mean, there's something else that I want to see if it's statistically significant. I even named it so it would be obvious. Yes, the left out terms. Okay. So I want to ask the question, are the left out terms statistically significant, right? And so that'll be this one here, okay, over this one here. And that will be the F ratio calculated, asking the question, is that stuff that I was not able to fit relative to how much I didn't fit. So this is kind of like the variance, if you will, associated with what I didn't fit. And I'm going to compare that to the true experimental error of the system. Okay? And I'm going to ask the question, is what I did not fit statistically significant compared to how good the data set is? And if I find out that that number is big, it means that there was structure that I didn't fit. There was stuff that was in there that had functional behavior, something going on in there. My model couldn't capture it because it was big relative to the variability of the data. If I have really crappy data, of course, that ratio is going to be small. And when it's statistically insignificant, what it means is I can't justify a model with more adjustable parameters. It will fit that. That's correct. Every time that I take another adjustable parameter, it just gets better compared to that. And this gets smaller, and so it's everything. But what I'm saying here is it's only by this successive examination can I tell myself that, yes, although I can make it fit the data better, I can't justify an additional adjustable parameter. The data is not good enough. So what do you do as an engineer at that point?
Logarithm.
What?
Logarithm.
You can go snowball fight? Is that what you said? No, it's all snowballs. What? No.
Take the log.
It means you need to go back to the lab to get better data. You can futz around with models all you want, but if the data doesn't justify more adjustable parameters, it doesn't matter. You can throw any model you want at it, and it won't get any better. You'll only get better if you figure out how to get a smaller, true error. Done.
So yeah, I realized the lecture was here at 1:35. And I was like, because I got the good deal.
time.